suppose we have a function of two variables. Now, how can we find the maximum or minimum of this function? So, for example, if I have f of x comma y equal to x squared minus 2x plus y squared, this doesn't have any maximum because you can plug in some large values and make this as large as possible. For example, I can plug in 0 for x so that it goes away, while plugging like millions and trillions into y, and that will make this function increase to infinity. Right? I can make it as large as possible. There cannot be any maximum for this function. However, this does have a minimum. And I can show you that by doing algebraic manipulation of the right side, but that won't be the usual method that we're going to use, okay? But just for demonstration purposes, I'll try to do it, find out the minimum using just basic algebra, okay? So here's what I do. I can rewrite this as x squared minus 2x plus 1 minus 1 plus y squared. These two are the same thing, right? Because if you add 1 and subtract 1, it's the same thing. And what I want to do really is to complete the square. This is a square of what? It's a square of x minus 1 squared minus 1 plus y squared, isn't it?
Yeah.
Okay. So we call this completing the square in pre-calculus. You learned it. But the reason I'm doing it here is to point out the following fact. Can x minus 1 squared ever be negative? Anything squared is positive or 0. The minimum it can be is 0, right? How about this one? Again, 0 or positive, right?
Yeah.
So the minimum value that this function f of x can have is when this is 0 and when that's 0, which gives you negative 1. When does f attain this negative 1? When x is?
0.
No, when x is?
1.
1. 1 minus 1 is 0, right? At 1 comma 0, you're going to get the value of?
Negative 1.
Negative 1. And we know that that's the minimum. Now the problem with this is that it only works for quadratic functions. If we play with something else, like say function that has like quartic, or in some cases cubic, and if we have sine, cosine, any other complicated functions, you can't argue using this method. Okay? So instead of that, what we need to do is to use calculus. Now, how do we use calculus? First, let's try to imagine the graph of this thing. Now, z equal to x squared plus y squared. What kind of surface is this?
Plane.
It's a...
Oh.
No, it's not a plane.
Circle.
No, okay, its level curves are circles. Yeah.
Circle. No.
What kind of surface is it? Circles are curves, not surfaces.
A paraboloid.
Paraboloid, right? So it's like this. It's a paraboloid. Now, if you know that that's a paraboloid, you can figure that out by drawing the level curves and also x and y traces. Okay. Once you know that that's a paraboloid, then you can go and look at this and say, hey, I have x here, and I have x minus 1 here. What does that mean? The entire surface is moved one step in which direction? Positive x direction. Okay. One step in the positive x direction. Okay. So you're moving one step that direction. And what would this minus 1 do?
Move it down.
It will move down by 1. So it's going to move down by 1, so you're going to get this. Okay? And this lowest point here will be this point, 1, 0, negative 1. And that's why that function has the minimum value -1 at x equal to 1 and y equal to 0. So you can kind of see where that's from. Okay, so here's the paraboloid, and the minimum point is this. Now let's think about the rate of change at this point. Now, what would be the directional derivative in the x direction at this point? Well, what's the partial with respect to x? Partial with respect to x is same as the directional derivative as you're moving in the x direction. See, if you look at the xz trace, z equal to x squared is like this. No. Sorry. If I look at the xz trace, z equal to x squared minus 2x, it looks like this. It's like this. That's the xz trace, right? And we're really trying to find the derivative in the x direction at that point. What is it? Okay, you can calculate 2x minus 2, but if you evaluate at 1, 0,
It's -1.
no, 2x minus 2 evaluated at 1, 0, what is it? 0. But you knew that because derivative is the slope of the tangent line, right? What's the slope? It is a horizontal slope, doesn't it?
Yeah.
Right. So it's 0. Okay. So the same kind of logic applies just like the function of one variable at the minimum. At the minimum point, you momentarily stop, you turn to go up again, right? So right before that minimum point, the derivative is negative. Right after that minimum point, the derivative is positive, right? If you're passing through a minimum region like that, right? Just before heading to the minimum, the rate of change is negative because you're going down, right? And right after passing the minimum, the rate of change is positive because you're going up, right? Therefore, exactly at the point when it's the minimum, it will be between a negative and positive. So what value can it be? Must be 0. Okay? So that's how you can think of it, right? So we have a hunch that if we calculate the directional, the derivative in any direction, so the partial derivative of this function will be 0, whether you differentiate by x, or differentiate by y, or differentiate in any other direction. Okay? It will always give us 0. Okay? What does that mean for the gradient itself? What's the gradient at this point? If the partial with respect to x and partial with respect to y is 0, what do we know about the gradient? What is it? It's, what's a gradient again?
Dot product of.
No. That's,
Oh.
use the gradient to find the directional derivative by doing the dot product with the vector. But that's not what the gradient is. What is a gradient?
Partial.
It's just simply vectors made of all the partial derivatives, right? But what did I just say about the partial derivatives? They're 0. So what can be the what is the gradient then?
0.
It's a 0 vector. That's what we know. So by this heuristic argument, we can say that, I don't like this squaring, complete the square method. Okay? I'll just find the gradient, and I know that at the minimum point, the gradient must be 0, so I'll just use that. Okay? So let's do that. So let's find the gradient of that fxy. And what is that? That's what's the gradient of this function? What is it?
2x minus 2.
2x minus 2, comma 2y. Okay? And when is this equal to 0? Well, when we say it's equal to 0, I mean 0 as a vector. When is it equal to 0? when 2x minus 2 is equal to 0, and 2y is equal to? Solve this. What do you get for x?
1.
What do you get for y?
0.
Okay, so that's exactly the point. 1 comma 0. That's where it attains its minimum. Right. So here's the lesson learned here. At the minimum, or same thing applies to the maximum, just like in one variable case. At the minimum or max of fx comma y, gradient of fx comma y must equal to 0. Well, I really mean 0 as a vector, meaning 0 comma 0. Okay? Must equal to 0. Now, I have to write this statement with a condition. The condition is if gradient of fx comma y exists. So that could be an issue sometimes because not all functions have gradients. If you recall calculus 1, we learned that all maximum or minimum of a function occurs at the critical point. If the maximum or minimum is attained inside a given interval, it occurs at critical points. Now, do you know the definition of a critical point? What's a critical? By the way, back then we used the word critical number. Here we say such point is a critical point because it's x comma y. Okay? But what's a critical number? A number where?
Across the x-axis.
No.
A number with
Change
direction.
Changing direction is somewhat right. Yes.
Inflection point.
No, the inflection point and critical numbers are different. What's a critical number? Can anyone give me the definition of a critical number? Yes.
Goes from positive to negative or negative to positive.
Okay, well, it's somewhat right, but I
In
want...
which the derivative of the function is
Discontinuity?
Okay, so everyone seems to have some form of vaguely correct answer, but you're not giving me the answer I want. So the correct answer is a critical number is where f prime is equal to 0 or f prime does not exist. Thank you. Okay? It's actually 2. Right? So let me repeat myself again. In calculus 1, you learned that a critical number is a point where f prime is equal to 0 or it does not exist. We have to include this extra case where f prime does not exist because there are cases where you have a cusp where you might have a maximum. The derivative doesn't exist here, but you might have a maximum. Okay? So the same kind of principle happens here. We have the definition that a critical point of a function f, or maybe fxyz, is a point x naught y naught such that the gradient of f x naught y naught, evaluated x naught y naught, is equal to the 0 vector or does not exist if it's not differentiable. So if you have a function which is not differentiable, or if its derivative is equal to 0, you call that point a critical point. Now, why are we interested in critical points? Because at the critical points, you will, if f has a maximum or minimum, it has to attain its critical point. It has to attain its maximum or minimum at the critical points. Okay. So once you have this, then the important statement is theorem. F attains its max or min at critical points. Now, one more thing that we have to remember is in Calculus 1, we also learned something like the relative max, relative min, and the absolute max and absolute min. Okay? So we can. So how does this work? If you have an absolute maximum or absolute minimum that's inside some interval, then that's also a relative max or relative min. So relative, I can change this statement to say f attains its relative max or relative min at critical points. So this is the case when the function is locally maximum around some neighborhood. So if you have a function which is like, if it has lots of ups and downs, and then at some point it might be maximum, but it might still be smaller than the highest mountain, right? So in that case, you call this a relative maximum. Okay? At those points, for those kind of relative max or relative min to work, to happen, it actually has to be a critical number. Okay? So that's the important thing that we learned.